better works in the vertical mode. I think the camera is confused because of my Santa Claus hat. Okay, excellent. Then welcome everyone. My name is still Matthias Magdowski. I'm a notable nodal voltage analyst at the Otto von Guericke University of Magdeburg in Germany. And I will switch over to my slides today. So, as discussed, the head of our chair is unfortunately sick today and cannot make it, so I'm here to replace him. And the topic for today is, as said, nodal voltage analysis. And before we start, also somehow fitting to my head, I have a nice survey for you on a scale of Santas. Ho, 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 how are you today? And you can scan this QR code and go to this website, particifyisalsa.de. And I think you can also go there and somewhere type in this number, but of course it's way, way, way easier to scan this QR code. And for a moment, I will disable my camera view so that all the 9 centers can be seen also in the recording and in the stream. And as there are no cameras pointing at me anymore, I will maybe go to this website, and I think I need to go there and maybe switch to full screen mode. And then we have 5 answers already, so let's take a look at the centers back again. There's a very bored center, there's a drunk center, there's a surprised center, there's an even more drunk center. There's a very unpolite center, a center that obviously has troubles with his Christmas lighting decoration. A center somehow defending itself, a sleepy center, and some center that is looks to be very hungry. So let's see what is the favorite center for today. We have 10 answers. I think we have more people in the room. Not everyone has decided yet, but there we have 12 answers. And there are 2 favorites, the number 6 and the number 7. So let's check back again. Okay, the number 6 is the one that has, and this is maybe what we can do next week. Next week I will also bring some Christmas lights and we can do some experience with Christmas lights. And yeah, we are living in challenging times. So also Santa has to take care of this. Okay, thanks for this. Yeah, so then let's come to the technical topic. So I think last week you've discussed about electrical networks and network structure and so on, and somehow talked about branch current analysis. Is this right? Okay, and then I remember, because this is the time when I entered the room, that Professor Fick was starting to discuss about nodal analysis, right? Okay, so we will jump right into this topic. And let's say for this method of circuit calculation or network analysis, there is kind of a recipe. I mean, at the end, you need to remember this recipe. You also somehow need to understand how it works. But okay, let's take a look at these steps, and they are displayed here as a summary. So we have a network. The network has a certain number of nodes, and we define one node as a reference node. Why is this meaningful? Because only then we can define these nodal voltages that we will see in a second. And if a network has a certain number of nodes, let's say k nodes, how many independent nodal equations are there? How many of them are linear independent that will give us a system of equations with linear independent equations? K minus 1. Yeah, so if we have k nodes, there will be k minus 1 independent nodal equations. And if we set one node as a reference node, this is the node that we kick out of the equation system, let's say. Okay, so then we express all the branch voltages and all the branch currents in terms of these nodal voltages. What this is, we will see in a second. And in these equations, as we will see, so the current is voltage divided by the resistance. We would always have this 1 divided by the resistance, 1 divided by the resistance. And because we are lazy in writing, we use conductances conductances instead of resistances. Okay, so then we set up all the node equations or nodal equations except for this reference node. And then we get a system of equations. We can solve the system of equations and obtain these nodal voltages or node voltages, the voltage from each node with respect to the reference node. And yeah, they are not really the final result. There are some intermediate result, but from these nodal voltages, it's quite easy to calculate all the branch voltages and all the branch currents that we would like to have at the end. So my idea would be to take a look at this at some example. And as an example, we will use this very simple circuit. And we can do also some experiment with this later. And so the idea is that, okay, if we calculate current and voltage in the circuit, and especially if we have this source here on this side, and if we would calculate the total voltage at the end, the ratio between the total voltage and the source current gives us the equivalent resistance. That's a question.
Yeah,
no.
You might be using an old set of slides, or maybe we have an...
Yeah, I'm using the more interactive version of the slides, let's say. There is a slide version that has more information in there, but it's very boring to just read what is written on the slides. That's why I have a different version of slides that allows me to do for more interaction, right? Okay, so don't be. I will share the slides later. I had no time to share them in advance, but I will share the slides later. So we have the circuit. If we take the ratio between the total voltage and the source current, what do we get? A resistance, and we get the equivalent resistance of the circuit. And so if you would calculate the equivalent resistance, I think this is what we have done last time. Of the circuit, what would we do? How would you calculate looking from the direction of the source, how could we calculate the total resistance of the circuit? Yeah, so this is a series connection, this is a series connection, and then we have the parallel connection of the two. Okay, and so now we want to do this with this nodal voltage analysis. So yeah, at first we number the nodes. I set this node as a reference node, 0, and call this node 1, node 2, node 3. Then we can define these nodal voltages. So this is the voltage, these are the voltages going from each node to the reference node. So we have a voltage, a nodal voltage V10, V20, V3, 0. Okay, and so then the next step would be to formulate a system of equations for this. And to do this, I will somehow copy this and, or let's say do a screenshot. And then I need my drawing program here, which is called Windows Journal. Quite old program, but very convenient for me. Paste this in there and make this a little smaller. And so let's say our final goal, what we want to do is we want to calculate the resistance at these ports. So the resistance, let's say from node 1 to node 0, the total resistance of the circuit. And as you said, it's R1 plus R2, series connection of them. And then in parallel, we have the series connection of R3 and R4. Okay, so this is the final result that we want to get at the end. And so nodal analysis should also give us this result at the end. So at first, what we do, so if we go back to our recipe here is, we have defined the reference node, we have done all the stuff, and now we need to set up node equations for all nodes. And to do this, of course, at first, it would be a good idea to define the direction of currents. So I just define all the currents going downwards. And so our nodal equations at the first node, so we have this current flowing towards the node, and we have these two currents, I1 and I3, flowing away from the node. So I will write I1 plus I3 should be the same as I source, right? Okay, so for the second nodal equation, it's not really a node yet, but what I can tell you later is, and this is also a bit the motivation for why do we do this with nodal analysis. Let's spoiler something in between. What we will do later on is we will add some resistor here that I will call R5. And if we now take this resistor R5 into account, and once again we want to have the total equivalent resistance of the circuit, how we do the calculation then? Anyone some idea? This resistor R5 is a really nasty one. It will not get any presents for Christmas because this resistor R5 is destroying each and everything in our circuit. The resistor R5 makes that these two resistors are not in series anymore because there's not the same current flowing through these resistors, because there can also be a current flow through this resistor. And the same is here. So they look like they are in series, but they are not in series anymore. And this branch and this branch, or let's say this resistor and this resistor, they look like they are in parallel, but they are also not in parallel because there's not the same voltage drop across these resistors, because there can be a voltage drop across this resistor at the center. And so in the same way, these two resistors are also not in parallel to each other anymore. So this is a not too complicated circuit, but still a circuit that has no pure parallel and series connections that cannot be calculated this way. So how could we still calculate the equivalent resistance of this?
Flash equations?
Yeah, maybe with nodal analysis. Yeah, let's say this should be our motivation to use nodal analysis. Maybe nodal analysis will help us in calculating the total equivalent resistance of the circuit. And for this later on, we will really have a node here and a node there, but at the moment we don't have this. No? At the moment, forget about this red resistor R5. So at the second node, we can say, okay, the current towards the resistor and the current away from the resistor both together must be 0. And I will write it like this, that the current towards is positive, the current flowing away from the node is negative, and both together should be 0, right? Okay, and for the third node, the equation would be then who has an idea? I3 minus I4 should also be 0. Okay, so now we have set up some system of equations with 3 equations for our 3 independent nodes or linear independent nodes, but we have a system with 4 unknowns that cannot be solved yet. We have 3 equations, but 4 unknowns. Okay, so we need to do something. And the next step would be to express these currents here all in terms of these voltages. So we have a voltage V1, we have a voltage V2, V3, and this is V4 and V3. And so for each voltage, where do I have some space? Nowhere. So for example, the fourth voltage here could be expressed as I4 divided by R4. But it's easier to write G4 times I4 because then I don't have to write 1 over R all the time. Okay, so this equation then will be G1 times I1 plus G3 times I3 still equals the source current. So then we will have G1 times I1 minus G2 times I2 equals 0. And for the last equation, we will have G3 times I3 minus G4 times I4 equals 0.
Sorry?
And yeah,
I think you switched voltage.
I switched voltage and current, so I need to delete lots of stuff.
Isn't I1 and I2 is equal?
Yeah, and I1 and I2 is equal now, but later on they won't. But very good point, of course. Speaking and writing at the same time is always a challenge. This should be all voltages. Very good point. And at the moment, also very good point, this current and this current is still the same. This current and this current is also still the same. But later on they might not be. Okay, still looking at this, we have still 3 equations. How many unknowns do we have? Still 4. Now comes, going back to our recipe, now we express the branch voltages. We have expressed the branch currents in terms of branch voltages. Now we will express them in terms of these node voltages. Now comes the, let's say, the trick part of this method. So we will say our first voltage, this one here, can be calculated by the difference of this voltage minus this voltage. So V1 can be expressed by the branch voltage V1 can be expressed by the nodal voltage V12 minus V10 minus V20. Right, so this one plus this one should be this one, or this one is this one minus this one. So the second branch voltage is the same as the second nodal voltage. The third branch voltage, this one here, is the difference between this and this. So V10 minus V30. And the last and fourth branch voltage is the third nodal voltage. And so now we will take this set of equations and insert it there. And then we get some longer set of equations. Luckily, I have some space here. So G1 multiplied with V10 and then minus G1 multiplied with V20. This is this term. So then we have plus G3 multiplied with this one here. So V10 minus G3 times V30 still equals the source. So then we can take a look at the second equation, G1 times V20 minus G2 times, oh no, this was, this should be V1 here, right? You really have to be careful. I do lots of mistakes in calculating. You have to triple check everything. So this should be V1 because this was here this node equation. No set here it was I1. Okay, so G1 multiplied with V10 minus G1 times V20 and then minus G2 multiplied with V20, and this at the end should still be 0. Okay, and so then we have the last equation. So G3 multiplied with V10 minus G3 multiplied with V30 minus G4 multiplied with V30 and still is 0. And so now, looking at this, what have we achieved? We have an equation system with 3 equations and 3 unknowns, namely the 3 nodal voltages V10, V20, and V30. I will have something in my tongue later. So now what I will do is I will just rewrite this equation. Do you spot some mistakes somewhere? No, okay. If you, please make me aware of. So now I will use this space here to rewrite this set of equations in matrix form. So we have the matrix with all the coefficients, then we have the vector of the unknowns and we have the vector of the sources, or let's say the right-hand side of this equation system. So here we have the three unknowns, V12, V10, V20, V30. Here we have the sources, or the right-hand side. And so now on this side I need to check. So related to V10, we have G1 and we have G3. So here I can write G1 plus G3. Then we have minus G1 that is associated with the second nodal voltage and minus G3 that is associated with the last nodal voltage, right? Okay, so in the second line I will do some trick. I will change all the signs here. I will make this plus and this minus. So we have a minus G1 that is here for the first nodal voltage. And we have a G1 and G2 that is related to the second nodal voltage. And we have nothing that is related to the third nodal voltage. And in the last line, I will also change the sign, make this minus to a plus, this minus to a plus, and this plus into a minus. So we have minus G3. Then we have nothing that relates to the second nodal voltage, but G3. This is a multiplication dot. G3 and G4 that are multiplied with the third nodal voltage. So this is our system, our set of equations that we obtained for this circuit using nodal voltage analysis. Okay, so now if you look at this set of equations and at the same time if you look at this circuit, what do you see? Do you see something? Do you see some rules or some patterns? Yeah? So here we always have something plus. On the main diagonal here we always have something negative. And let me maybe in gray or so number the rows and number the columns. And now we can check, okay, in the first element of the main diagonal, we have the G1 and G3. Here we have G1 and G2. Here we have G3 and G4. If we are taking a look at the first node, the resistor R1 and the resistor R3 are connected. At the second node, resistor 1 and 2 are connected. At the third node, resistor 3 and 4 are connected. So what would be the rule to set up the elements on the main diagonal? It's always the sum of the conductances that are connected to each node. Right? At this node we have these two resistors, that's why we have here G1 plus G3. At this node we have R1, R2, that's why we have G1, G2. Here we have R3, R4, that's why we have G3, G4. On the main diagonal, it's the sum of the conductances connected to each node. Okay, so if we know this rule, we can omit all these derivation part and directly set up the system of equations. So this is just shown to show you how it works. Yeah, but at the end, if you know the rule, you can directly set up this. Okay, so there's one rule for the main diagonal, then we need to have rules for the off diagonal or for the secondary diagonal elements. Does anyone spot the rule or see the pattern?
For which one?
Say again?
For which one?
For the off diagonal elements, for this one here or for this one, for this one, for this one. Why do we have a 0 here? Why do we have minus G1 here, minus G3 there?
So if we look at in the matrix at the spot 2, 1, it's at node 2 and the resistance of the resistor.
Exactly. Between node 1 and 2 we have the resistor R1, and that's why in the first row, second column, or second column, first row, you know what I mean? We have this conductance, and they are always negative. Between the first and the third node, we have this resistor, R3, And that's why we have the G3 here and there in the first row, third column, third row, first column. And between 2 and 3, we have nothing at the moment. Later on, we will connect our resistor R5 there. That's why we have here 0. So on the off-diagonal elements, it's always the coupling conductance, the negative coupling conductance between the two respective nodes. And here, what could be the pattern here in our source vector?
The source and then 0.
Yeah, so we have the source that is connected to the first node. That's why it's showing up in the first row here. At the second node and third node, we don't have any source. No source connected here, no source connected there. That's why it's 0. Right? Okay, so there we have our system of equations. And there we have a summary of these rules for the main diagonal, for the off diagonal, and for the source vector inside this matrix and inside the vector. So then we can have some values. And in my example, because this is later something that I can also show in the experiment, I have 1 kilo ohm and also 3 1 kilo ohm resistors, 1 2 kilo ohm resistor, and let's assume we have a source current of 1 ampere. So then we can convert these resistors into conductances and set these values into our system of equations. And then the system of equations looks like this in matrix form. And so then the question is, how can we solve this system of equations? Easily. Say again? Yeah, we could take, let me see if I have some space somewhere here where I can write this. So if we summarize the system of equations, right, then it looks like this, that we have our G matrix that is multiplied with the nodal voltages. And on the other side, we have this source vector. Let me have some space here. Right? This is the matrix, this is this vector, this is this vector. And so we know this vector, we know this matrix, the coefficients inside this matrix. We want to have this vector. This is the unknown one. So what we do is we take the inverse of this G matrix and multiply it from the left-hand side. And if we do it on this side of the equation, we of course also have to do it on the other side of the equation. And the inverse matrix times the same matrix is the identity matrix. And the identity matrix multiplied with the vector is the vector itself. So we can skip this here. This will just be the vector, and the vector is the inverse of the matrix multiplied with the source term. This is how we solve this system of equations. And so this is also what is written in my slides. So we get the nodal voltages if we take the inverse of the matrix and multiply it with the source vector, and then we should get a result at the end. So, and then the question is, of course, how we do it. So what would you suggest? To solve such matrix equation and the corresponding set or system of equations, how would you solve something like this? What tool would you use? Yeah, a determinant, but of course we would do it in MATLAB, right? or in the corresponding software. We would not do it by hand. So I have proposed that let's do a solution in MATLAB. Who has used MATLAB before? Okay, at least one person. I think I won't use MATLAB because MATLAB is always horribly slow on this computer here. So I will use Octave. And there is GUI here. And this is what I will open up. And then switch back to my drawing program and Okay, and there's Octave starting. Who has used Octave before? No one has used Octave. So Octave has the advantage that it's a free and open source program and has the same syntax as MATLAB. And so you can use this free of charge. And it's also working quite nicely. So I will try to make this window a bit smaller so that I can fit everything here on the screen. And maybe go back to my slides at first, because here I have the values printed. So at first we need to have these values. So R1 is 1 kilo ohm. How do I write kilo in such a mathematical program? Does not work. Yeah, so, and the easiest way to do it like this. 1E3 gives 1000. Okay, the same, no, R2 should be 2 kilo ohm, and R3 is not 1, but 1E3, and R4 is also 1E3. Okay, so then I have these 4 resistors. So now I need to convert them into conductances. So G1 is just the inverse of R1. Yeah, and we get the 1 millisiemens. The same I do for G2 and G3 and G4. And my source voltage, source current should be 1 ampere. Okay, so there I have all the values. So now I can go back to my matrix here. And now I need to insert this matrix. So I will call this G matrix. And matrices can be inserted inside these square brackets. And we can just write the elements. So this would be the first element. Comma is the element separator. This would be the second element. This would be the third element. And if I want to have a new row, I need to use a semicolon. So in the second row, I have minus G1. Then I have G1 plus G2. And 0, and in the last row I have minus G3, 0, and G3, and then the space is a bit limited, so I maybe make this a bit smaller. G3 plus G4, closing the square bracket, and there's my matrix with the values. And we can check that this is also what I have here on this slide. Yeah, if you compare the numbers, it should fit very well to what we have here. So 2 minus 1 minus 1 minus 1, 1.50 minus 1, 0, 2 fits. Okay. So then I need to have the source vector. And inside the source vector, I have the source and a 0 and a 0 in 2 more rows. So this is my source vector, 1, 0, 0. And so now, coming back to the solution of this system of equations, I get my nodal voltages as a vector by multiplying the inverse of the matrix with the source vector. So I get the nodal voltages as a vector from the inverse of this matrix multiplied with our source vector. And yeah, I would just calculate it, and there's the result. So now we get the 3 voltages that are written here into our circuit. This voltage, and this voltage. So this voltage is, of course, if we push a 1 ampere current through a couple of kilo ohm resistors, we get kilovolts of voltage, but we get 1.2 kilovolt here and 800 volt here and 600 volt over there. And so now if I would calculate the equivalent resistance or the total resistance of the circuit, I could take the first of these nodal voltages, right? The total voltage divided by the source current. So if I take the first of these voltages and divide by the source current, I get, of course, 1200 divided by 1 is 1200. If I would calculate the total resistance using the formula that we have over here, so once again, I will quickly write some equation or some function for the parallel resistance or the parallel connection of two resistors. So if we have two resistors in parallel, how would you calculate the parallel circuit? Yeah, the product of the two divided by the sum. And so now we can also calculate the total resistance, and it should be R1 plus, no, it should be the parallel circuit of R1 plus R2, and the other branches R3 plus R4. And then I've once again did something wrong because I pushed some button in between on my keyboard that I should not have pushed. Plus R2 and R3 plus R4, and it's always easier to retype than to find the mistake. Okay, and there we get also 1200 ohm. Okay, so nice. Yeah, so now we have a method that at the moment looks a bit complicated, right? It looks a bit cumbersome just to calculate this equivalent resistance here, but it works. It gives us the same result, which is nice from my point of view. I don't know if you agree, but I appreciate this. I like this. Okay, so we have some result. We have solved this in MATLAB. Now we could do a comparison with some measured equivalent resistance. And for this, I've already opened up my document camera here that I have here on my table. I will enlarge the image a little bit. And you can see I have a nice multimeter. I will maybe move over a bit. And luckily my camera is tracking me. So here's my multimeter, and it can be switched on, and then it can measure resistance. And as you can see, this is always the problem. You always get some nasty reflection from the lights at the ceiling. But it's showing overload at the moment because nothing is connected. If I connect the two wires together, then I measure 0.1 ohm because this would be the, let's say, the resistance of this connection and of these measuring cables. Okay. So I can measure resistance, and then I've brought some box here, one of my many experimental boxes. And inside this box, as you can see, I have something that on the other side shows 1 kilo ohm. So it's a box with 1 kilo ohm resistors, and I will just grab 3 and put them on the table. 3 1 kilo ohm resistors, and then I have a box where you can see I have 2 kilo ohm resistors, and I will grab one of these 2 kilo ohm resistors, put it somewhere else to not confuse them. And then inside this box I also have small breadboards, so I will take out one of these breadboards, and inside the box with the breadboards I also have 2 short circuit connections that are handy later on. And I have some more cables here that I can use as adapter cables for my multimeter for the measurement. Okay, so enough components. Now we can try to put the circuit together. And maybe let's move this over a bit to this side. This is always the nice thing here, that you can somehow rearrange the windows as you like. So now I would like to have this circuit, right? And maybe I will make everything a bit larger. So this was the 2 kilo ohm resistor. This is what I will put somewhere here. So there's my 2 kilo ohm resistor already. And then I have a 1 kilo ohm resistor on this side. And then sometimes they are bending their legs, and I forgot my calipers today. But I think it should be connected. We will see later on. So there's 1 kilo ohm resistor, and on the other side I also need to have a 1 kilo ohm resistor and another 1 kilo ohm resistor. Okay, so there they nicely fit. Now what we can do is maybe we can try to measure these resistors first if they really fit. So I connect one cable, one red cable to this side. I mean, for measuring resistors, it does not really matter. One black cable to this side. And so now I can maybe start over here measuring the resistance of this first resistor. This should give us 1 kilo ohm approximately. And then you can see these resistors are not perfectly accurate. The 1 kilo ohm resistor that is labeled as 1 kilo ohm. Here you can also maybe a little bit see it on the screen. The colors that it has the colors brown, black, and red. And brown is a 10, red, black is I think a 1, and red, no, black is a 0, and red is another 2 zeros or something like this. So there are color tables for this where you can check the meaning of these colors. At the end you get to 1000 ohm. Okay, so this was the, let's check again, this was the 1 kilo ohm resistor. So then I would just reconnect this cable. This is the 2 kilo ohm resistor. Oh, and this is really more than 2 kilo ohm. So I better replace this one. This will not really fit to what we calculated. It maybe accidentally got into my box here. So this looks nicer. This is a nice 2 kilo ohm resistor. And then on the other side, we have another 1 kilo ohm resistor that is now slightly larger than 1 kilo ohm. And we have, if I connect properly, we have another 1 kilo ohm resistor. Yeah, and as you can see, these gray ones, they're always a bit smaller. The other one is a bit larger. Okay, so now let's disconnect these cables first. Now, of course, we need to have, let's say, in our circuit, and in the experiment, we also need to have this connection here, and we need to have this connection. And therefore, yeah, I have this cable and this cable. So I will try to connect one here to make this short circuit. And it's a bit tight. Why does it not work? Oh, okay. There it worked. And I also need to do this on the other side at the right boxes. Okay, I think last time I used the yellow one. The yellow one is a bit easier to plug in. This one has really tight spring contacts. So there it worked. And let's see if I can also get this on the other side. Okay, so this is the circuit. There's my multimeter. And there the camera is focusing. And now if I calculate, or if I measure the total resistance from the top to the bottom, ta-ta, I get approximately 1.2 kilo ohm. As we calculated in LTspice, no, not in LTspice yet, in with our nodal analysis and what we calculated by hand, right? Okay, so this somehow works, and it's, of course, it's not exactly 1.2 kilo ohm, it's a little less, because as we've seen, these 1 kilo ohm resistors, they are missing some tens of ohms. Okay, so now let's add this bridge resistor. And as we've discussed before, this bridge resistor is a bit nasty, because now nothing is in parallel and series anymore. But luckily, we have learned about nodal analysis, right? So maybe nodal analysis helps us a bit in solving this problem, and I will switch over to red. So now we add this resistor to our circuit. And we remember these rules for our matrix here with the conductances. So what does change at this matrix? Say again? Yeah, so the zeros should go, and instead of the zeros, now we have a coupling conductance between these two nodes, so we should have the minus G5 here and the minus G5 over there. And say again?
Isn't it going to be a 4 by 4?
No, it's not going to be a 4 by 4 matrix because we don't change the number of nodes. We still have only 3 nodes.
2, 2, and 3.
Yeah, at this position we should have some additional G5, and at this position we should also have some additional G5. And in this sense, I mean, this is nothing that we discussed before, and some light is flickering in the room, which annoys me a bit. So what we have not discussed before is that one conductance, or let's say the conductance of one resistor, can only appear 4 times in the matrix if it is not connected to the reference node. So G1, G3, and G5, they all appear 4 times in the matrix, 2 times on the main diagonal, 2 times on the secondary diagonal elements. Yeah, so if I take some, maybe, I don't know, light color, so the G1 we have here, 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 and there. Yeah, and the this will be a very heavy color, but the G3 we have here, there, there, and there 4 times, and the G5, the red one, yeah, maybe this color is not too bad. The G5 we have here, here, and there. So they all appear 4 times, and the other elements, this one here, we just have there, and the last color that I have is maybe this one here, and this one only appears here. So if a resistor is not connected to the reference node, it will have 4 entries in this matrix. If a resistor is connected to the reference node, it will have just 1 entry inside this matrix. Okay, so yeah, we can set up a new system of equations. We can insert new values. Now for the resistor R5, I've selected 3 kilo ohms. So 1/3 of a millisiemens for this. And then we can insert the values of these components. And this is of course now what we can do and check in our Octave. So I will maybe try to move the window over here and make it a bit smaller. So yeah, or I think I also have the values there. Then of course we need to solve this, but I will maybe move this up a bit, then it's easier visible. So our G matrix now for the, including the resistor R5, so here we need to have a G5, here instead of the 0 we need to have a minus G5, here we need to have a minus G5, and here we need to have a plus G5. So that's nice, really, this is some advantage of this method. The circuit changes, something changes in the matrix, but still you are able to calculate it. It does not completely explode. If I enter, of course, now I will get some error message in MATLAB because I've not defined this before. So R5 should be 3 kilo ohm and G5 is 1 over R5. And then I can calculate this new G matrix. And then we can check, okay, this fits, right? 2, 1, 1. Just these values here changed. So this could be 11, 6. This is minus 1/3, minus 1/3, and this is 2.3. This works. So then we can solve the system of equations once again. So we can say the nodal voltages, including our resistor R5, is the matrix, the new matrix, multiplied with the source vector. Okay, before I enter and before I calculate the result, I would like to think you about our equivalent resistance of the circuit. So if we add this resistor over there, what should happen to the total equivalent resistance of the circuit? Should it stay constant? Probably not. I mean, it would probably stay constant if R1, R2, R3, R4, if they would all be equal, because then we have kind of a symmetric problem. If we add this fifth resistor, it would not break up the symmetry, nothing should change. But we have, this is 2 kilo ohm, the others are just 1 kilo ohm. So this side is different than this side. Now we add some resistor in the center here, this bridge resistor. Let's call it like this. So will the equivalent resistance get larger? Will the equivalent resistance get smaller? Yes. Why should it get smaller? A lucky guess, intuition? Who's for equivalent resistance will get larger? Okay, 1 or 2 persons, 3 persons. Who is for equivalent resistance should get smaller? Most people don't really cast the vote, I see. Okay, so the easiest way is we can try it out. We have all the measurement equipment here. So I will maybe a bit move over here, and luckily in my experimental box, the labels always flip over, but there is a box with 3 kilo ohm resistors, and I will disconnect the cables here at first, so the instrument will then show overload, and now I can connect the resistor here, and as you can see, this is a nice 3 kilo ohm resistor. Okay, so I will put the 3 kilo ohm resistor here at the top, and at first connect back the cables here, the measuring cables. So there's the result that we had before for the equivalent resistance of the circuit. That was not perfectly 1.2 kilo ohm, but a little less. We discussed this. Okay, so now I will take this resistor and I will place the resistor here at the center. And unfortunately, I need always both hands to do this, and will block the view onto the display of the instrument. But there's the result. And so what happened? It got smaller, right? It went down. The resistance went down. And yeah, if you a little bit think about this, it's also perfectly natural that it went down, because now we are giving, so we are trying to push a current with this current source through this circuit. And here the current sees a little larger resistor. If we have this bridge resistor, some portion of the current can go over to this side and sees less resistance here. And that's why the total resistance goes down. It's a little bit like if we are adding some parallel resistance to the circuit. That's why the total resistance goes down. Okay, so total resistance goes down. That's why also the total voltage go down that we calculate here. Or the total voltage should go down. Remember what we got before? Before we had these results, 1200, 800, 600. And so now if we calculate the new result, we get a little less total voltage, a little less voltage across the big resistor, a little more voltage across the small resistor, because, as we discussed, we are pushing current. So this voltage dropped down, this voltage also dropped down, but this voltage here increased, because some current is going this way through this resistor. And it decreased by, let's say, about 10 ohm. And now if we check back on our measurement, this is the result including the resistor. if I remove the resistor once again, and this camera here is really, really lightweight, it's very portable, that's why it's always flexing if I just barely move the table. Now, if I remove this resistor, resistance goes up by about 10 ohm. So this perfectly fits to what we just calculated. Okay, excellent. Yeah, so we have done a solution in MATLAB. We have done a comparison with some measured equivalent resistance, and this nicely fits. So now I have some more questions for you. And the first one is the nodal conductance matrix that we set up there, right? The matrix here, this matrix that is now nice and colorful, labeled like a Christmas tree decorated. Is it always square? Is it always invertible? Or is it always symmetrical to the main diagonal? And it should be the very same link. You can just continue on this website with the next question, and I will show it for a couple of more seconds because there are some more phones pointing at me. And then we can go and check the result. And of course, here there is some mention of the Matrix movie that, yeah, is unfortunately probably older than most of you, right? It's from 1999. Okay. I will not guess your age. So let's go to the website, check for the next question. And yeah, so it's always a square matrix. I mean, otherwise we would have more equations or less equations than unknowns, or vice versa, which does not make sense. So we always need to have the same number of equations as unknowns. It should always be invertible, because otherwise we cannot solve the system of equations. And it will also always be symmetrical to the main diagonal. Yeah, we can check this one here, or we can, I think I have some example here, the one from before, right? It's always, we can always use this, the main diagonal, as a mirror axis, and then if we have minus G1 here, we always need to have minus G1 there, because the coupling between, yeah, or what is in the first row, second column must also be in the second row, first column, and so on. Okay, so all of these answers are correct. And there's a second question. What is the advantage, or what are advantages of this nodal voltage analysis with respect to branch current analysis that you discussed in the last lecture? Is the system of equations solvable or can be solved using matrix calculation, or is the system of equations smaller and has fewer equations and fewer unknowns than usual, or the main advantage, or one of the main advantages, that there is no need to find some independent mesh equations, for example, using this complete tree method? And probably, oh, we have only 4 answers so far. Because you have no answer? You need to think about this more? Oh, now we have 6 answers. I will maybe wait for 10. Okay, and let's have a look at the result. So, yeah, so I think this answer, I mean, it's always to discuss, but I would not call this as one of the main advantages, because each system of equations can be solved by matrix calculation. You don't need to have nodal voltage analysis for this. Will also work with branch current analysis, mesh current analysis, whatnot. Usually the system of equations is smaller. In branch current analysis, you set up mesh equations and you set up nodal equations. Here we only set up the nodal equations, so we get a smaller system of equations, which is usually an advantage, especially if you solve the equation system by hand. Right? If we would now calculate this circuit with branch current analysis, we would have 3 nodal equations and we would have 3 mesh equations. So we would get a system with 6 equations and 6 unknowns, quite difficult to solve by hand. With nodal analysis, we only get a 3x3 matrix system or system of equations. This is definitely some advantage, but the main advantage is the last one, that there's no need to find these independent mesh equations. I've also summarized this here a little bit. Yeah, so we don't need to set up this complete tree. We don't need to find independent meshes. And this can usually be a challenge. And because of this third reason, the nodal analysis is the method that is used in all circuit simulators that are out there. So also in this LTspice, if you remember, that we used in the last exercise. So what is done there in the background is also nodal analysis, or some kind of modified nodal analysis that can also handle voltage sources and not only current sources. Okay, so then I would, for the moment, skip the mesh current analysis to save some time, and at first go to the superposition method. And for the superposition method, to explain this, I have prepared, and I mean, you have probably had a look at the slides before because you were confused that I was using different slides. I've prepared some Kahoot quiz, and hopefully my browser is still logged in or would allow me to log in quickly. Yeah, and as usual, my computer's a bit slow, but there we have it already. The answers are blanked out here so that no one can spy the answers already. But I need to log in first. But there is my login. And then it's loading. And yeah, okay. And we will wait until it's loading. And now we can host it live on my computer. And have you played this before from time to time? You know how it works? No? Then I will explain it in a second. So I think we have 12 questions related to the superposition method or superposition theorem. And as you can see in this animation, there are usually 4 answers. So you will see the question and the answers on the screen, but at first, of course, you need to log in. So there is the game pin loading, and you need to go to this website, www.kahoot.it, or of course, you can scan this QR code. And then I also need to activate the music. And excuse me, I need to switch the audio output to the HDMI so that we hopefully, possibly also have the music in the room. And I will make the QR code once again a little larger and check if we get some audio in the room. Unfortunately not. So then I need to bring the audio back to my computer while you are logging in. So the Crestron audio display output is not working, but we can have some music here. Okay, and people are logging in, and while people are logging in, I will quickly switch to full screen in the recording and in the live stream. Because I can announce the prizes. Of course, I've brought some prizes. And the prize, so I have 3 prizes. Whoever wins can select the prize, and then the second can select, and the third can select. So the one of these prizes is a nice PCB ruler from a company called Wirth Elektronik, a German company. You can measure something, and there are lots of markings on there. We can measure cables and see the footprint of components and stuff like this. Then also from this company, I have a deck of cards. Skat. I don't play Skat. And it says it's with the French images. I don't have a clue about this. Yeah, but a nice deck of cards. And I always need to carry lots of stuff. So there's a nice bag, a tote bag, that I brought from a company. No, that I brought from not from a company, from a conference. So it's not fitting on my screen. It's from the EMC Europe conference that was in 2003 in Krakow in Poland, a conference that I visited. So we have 3 prizes, and we have now 14 people already logged in. And with this, I also need to switch to my original playing Kahoot glasses. Okay. So now we have 16 people. Everyone logged in? Anyone needs more time? Some phones still restarting? No? Okay. So, according to the superposition theorem, we have questions. You will see the question on the screen. There are 4 choices to answer them, and you need to push the corresponding button in the corresponding color on your screen. So how does the superposition principle work? We only switch on voltage sources, we only switch on the current sources, we only switch on one of the sources at the time, or we only switch off one of the sources at the time. That is the question. That is the question. Only switch on voltage sources, only switch on current sources, only switch on one source at a time, only switch off one source at a time. And the yellow answer is the right one. So superposition works in a way, right? We have a circuit with many sources, and if we only switch on one source at a time, then it's easier for calculation. And for every source, we do the calculation using current divider rule, voltage divider rule, whatnot. And then at the end, we sum everything up. Okay, so Diono was the fastest with the correct answer, taking the lead, followed by Vali and the center. Another center in the room, it's not me. So the next question is, if you switch off a voltage source, what does the voltage source will become? Will it become an open circuit? Will it become a short circuit? Will it become a resistance or conductance? Or will the voltage source turn into a current source? Okay. Oh, only 3 persons with the right answer. So the rule that you can remember is if you switch off such a source, you always remove the ring, or you remove the circle. And if we remove the circle from this voltage source, it will be a short circuit. And it is a short circuit, or it will be a short circuit, because a voltage source, an ideal voltage source, has 0 or very small internal resistance. Yeah. Maybe you're half right. Maybe I should, I mean, on the picture, it was clearly an ideal voltage source. Maybe I should, you're right. Maybe I should later on add, if you switch off an ideal voltage source, then it becomes a short circuit. Okay. Never mind. Center is now taking the lead, followed by something that I cannot really pronounce. The Really Hungry? Really hungry. Yeah, someone is really hungry. Me too. But as I've announced last week, I will have a Christmas party later on, so I'm fasting the whole day to be able to eat really a lot. So now the next question is if you switch off a current source, what will happen to the current source? Will it become an open circuit? Will it become a short circuit? Will it turn into a resistance or conductance, or into a voltage source? And once again, it's an ideal current source. It's an ideal current source. So, yeah, it will turn into an open circuit. Remember, if we remove the ring, the circle, there is no connection anymore. Okay, so the really hungry person is taking the lead. Ono is catching up once again, and the X is climbing to the 3rd place. So we come to the 4th of 12 questions. What do you need to know if you want to apply the superposition theorem? Do you need to know about series and parallel connections of resistors? Do you need to know about the current and voltage divider rule? Do you need to know about Kirchhoff's current and voltage law, or the current and voltage relations and Ohm's law at the resistors? And this is a question where nothing could go wrong because all of these answers are correct. You need to know all of them. Because if you just switch on one source at a time, you still have a circuit that you need to calculate somehow. And for this, you need to know about all these rules. Okay, so Onno is taking the lead once again. Senta climbing up back to the 4th place. Now we see some circuits, and now the question is, from the perspective of the source, the resistor R3 and the resistor R4. So we are looking from this source. What are these two resistors? Are they connected in parallel, in series, or are neither connected in parallel or in series? And yeah, they are connected in series. Right? If we take a look from this source, if we switch off this source here on the other side, this turns into an open circuit. So these two resistors are just in series. Most of you have answered this correctly. So the X is climbing up to the 2nd place, followed by Jimmy. That is first time on the podium, if I've seen this correctly. We come to the 6 of 12 questions. From the perspective of the current source now, these two resistors, are they in series, in parallel, or neither connected in series or in parallel? Okay, so now we are looking from the side of this source, from the current source. If we switch off the voltage source will turn into a short circuit. And if this is just a short circuit, then we have the same voltage drop across this resistor and across this resistor. So they are connected in parallel. That's why the red answer is the correct answer. Oh, now Onno is really taking the lead. Jimmy climbing up to the 2nd place, but we still have 6 more questions to answer. So the 7th of 12 questions is, from the perspective of the source, the resistance R1 to the rest of the circuit. So we are looking from this source, how is this resistor connected to the rest of the circuit? In parallel, in series, or neither in series nor in parallel? Okay, it's of course connected in series, right? Looking from here, this is in series to all other stuff that happens here on the back. So the blue answer is the correct answer. And DX is climbing up to the 2nd place once again, pushing Jimmy to the 3rd one. And now we have Z3 on the 4th place. Now we are looking from the perspective of the current source and are asking, how is the resistor R4 connected to the rest of the circuit? Looking from the current source, the resistance R4 or the resistor R4 to the rest of the circuit is connected in parallel, of course. Excellent. So some question that now could also be answered by some quiz wiseness. But, DX is taking the lead. Jimmy climbing up to the 2nd place. But still everything quite close together, and we still have, I think, 4 questions to go. So what is the current divider rule for determining, and you have 60 seconds to answer this. So you can think about this a little bit. You can, of course, also check which result does not make too much sense. So we want to have a current divider rule, how we can calculate this current. first formula, second formula, third or fourth. And I will try to get something to drink in the meantime. Schnip. Okay, most of you with the right answer. So, current divider rule. As a reminder, if we want to calculate this partial current from this total current, we take the resistor in the other branch, which is R1, and divide by the total resistance of this mesh. And this is R1 plus R2 plus the parallel connection of R3 and R4. And this is exactly what is written here. So this is how the voltage divider, the current divider rule works. Oh, total change of the podium. Zitri climbing up to the first place. The really hungry person is still very good. Also hungry for correct answers. And we come to the third last question, question 10 of 12. How can the equivalent resistance of this circuit be calculated from the perspective of the voltage source? So looking from this voltage source, what is the equivalent resistance of this circuit? And all these equations always contain, of course, all the four resistors, but just with different combinations of parallel and series connections. And I mean, we can once again check. If we are looking from this source, we have this resistor R4 that is in series to everything else. And then these two, if we have an open circuit here, these two are in series. We have the same voltage drop from here as to here, so these two branches are in parallel, and then this one is in series as well. So we have the R1 plus R2 series connection, R3 in parallel, and then plus R4 in series. And that's why the formula 4 is the correct answer. And Onno is once again climbing into the podium, and everything very close together, just 300 points of difference. So we come to the second to last question for today. What is once again the current divider rule for determining the partial current from the total current? So the same circuit as before. This is the total current, this is the partial current. How can we calculate this partial current from the total current using a current divider rule? And please be aware that this current is pointing in a different direction than this current. Okay, and the second formula was the correct one. We can once again check. So if we want to have this partial current, we need to have the resistor in the other branch, which is R3, and then the sum of or the total resistance inside this mesh, which is just the sum of R1, R2, and R3. And we need to have the minus because this direction is different than this direction. That's why the second equation is the correct one. The blue answer, formula 2. And oh, we have Z3 and the really hungry person once again climbing up, and X on the third place. So now we come to the final question, question 12 of 12. Under which circumstances can the superposition principle be used as an advantage or used to advantage? If only one branch voltage or one branch current is of interest, if both current and voltage sources are present, if there are many sources in our circuit, or if the network also contains nonlinear components such as diodes. And the first two answers, as you can see, are the correct ones. So superposition makes sense if you just want to know the current and voltage at one position in the circuit. If you want to calculate all the currents and all the voltages each and everywhere, then use a method that uses some set of equations, and then you get, as a result, all currents and voltages. And superposition also works nicely if you have current and voltage sources at the same time. Not too many of these sources, but current and voltage sources at the same time. This would also work with branch current analysis, but the nodal analysis that we discussed only works with current sources, and the mesh current analysis only works with voltage sources. So this works in both ways, or in both cases. Excellent. So now we can have a podium and you can make some rrrm and some applause, because on the third place we have the really, really hungry person. On the second place we have DX. And on the first place, can be only one, there is Z3. Congratulations to everyone. So here are my 3 prizes that I brought. I will maybe make the audio a little louder. Oh, okay. So who is Z3?
What? Take the cards.
You take the cards. That's a good choice. You are X. You take the ruler. And who's the really hungry person? You are the really hungry person. Can I throw this? Yeah. Oh, okay. Excellent. Okay, then. Yeah, I would say we skip the example and we stop for now. So I will say thanks for your attention, and we will do a break now.